In today's video, here is a nice problem that was suggested by viewer. Here is a following setup for all n as a natural number or positive integer. Satisfy this following fraction. We get 3 to the n plus number 1 over n squared is an integer. Okay. So now, in order to get this problem solved, we are going to check the obvious solutions. We may have one solution, we may have more solutions. Okay, depends. So now I'm going to check if n equals number 1 is going to be a solution. So if n equals 1, it definitely is a solution because it is verifying this fraction. We get 3 plus number 1, which is 4, divided by number 1, which is 4, which is natural number. Okay. Now, before we check other solutions, we are going to go through two cases. So if n is a even and if n is a odd, what is going to be happening if n is a even? We may have no even integer here. Okay, so let's check that. So if n is a even, let's write this fraction on the form of the equation. So we get 3 to the n plus number 1 over n squared, which equals k, where is k is an integer or positive integer or natural number, is the same thing. Okay, so let's multiply both sides by n squared. So I get here 3 to the n plus number 1, which equals k is multiplied by n squared. So as we know, if we have n integer and then we square it, always we get n squared is a congruent to 0 mod 4. Okay, or n squared is a multiple of 4 always. Okay, so this one is definitely is a congruent to 0 mod 4, which means the left hand side of this equation it also is a congruent to 0 mod 4. Okay, so what does this mean? So we know, let's write number 3 as 4 minus number 1. So we get 4 is 0 because 4 divides 4. So we get here minus number 1 to the n, minus 1 to the n, plus number 1. As you know, if n is a even, which means this one is turned to number 1, plus number 1, which is 2. So we get a remainder 2. 2 is a congruent to 0 mod 4. This is definitely is not true because we get two different reminders. So this is impossible, which is contradiction, which means we have no even integer here, which means n must be odd. Okay, now let's switch that to odd. Is definitely is a odd. Now let's get rid of this one and work on odd integer. Now in this case, n is a odd. You will keep changing n as you going up. You will find this fraction cannot be integer. Okay, so for example, if you check n equals 3, you get 27 plus number 1, which is 28. 28 divided by 9, which is not integer. Okay, so and so on and so forth. So now we are going to prepare ourselves to prove we have no solution for this equation. Okay, but we have insufficient information here. We need to create something that can help us to get so what to do here, since we have odd integer here, we may have some intersection points with odd prime and odd integer. Okay, so what to do here, let's choose p can divide n at some points. Okay, but we are going to have a restriction point here. Okay, because p cannot divide any integer here. P as a prime cannot divide n at any points. Okay, but since as we going down with odd integer, we may have the smallest prime. Okay, the smallest prime is not necessary to be number 3. It could be anything here. Okay, it could be 5, it could be 7. So once you get the smallest prime which divides this n, we are going to stop. Okay, let's go through this one. Let p to be the smallest prime such that p divide n. Okay, if p divide n, which means p divide n square. Okay, and also remember here we get this fraction is an integer, which means n squared divides 3 to the n plus number 1. Okay, so we'll have also n squared divides 3 to the n plus number 1. This one is called transitive property. If we get p divide n squared divides 3 to the n plus number 1, which means p divide 3 to the n plus number 1. This is arithmetically p is going to be divide 3 to the n plus number 1. So which means 3 to the n plus number 1 is a congruent to 0 mod p, or 3 to the n is a congruent to minus number 1 mod p. So this one is going to tell us 3 to the n is a congruent to minus number 1 mod p. This is the statement number 1. Okay, another thing we can extract it from this statement, since we get 3 to the n is a congruent to minus 1 mod p, which means p cannot divide 3 to the n. Okay, this one p cannot divide 3 to the n. So this one also is verifying the Fermi-Taylor theorem. Okay, we get p as a prime, we get 3 to the n as an integer, which means according to the Fermi-Taylor theorem, this one is going to be written on this form: 3 to the n is a congruent to 1 mod p. Now let's call this one as a statement number 2. So also, since p divides n, implies p minus number 1 cannot divide n. Okay, we are going to work with the Bayesian theorem here. So we get GCD of n p minus number 1 equals 1. So for all x, y as a natural number or integer, so I'm going to take this one in particular. I'm going to take this one as a special case for the Bayesian theorem. So there exists n and p minus number 1 also as integers or natural numbers, such that we're going to write this one on the form of the Bayesian theorem. So we get x is multiplied by n minus p minus number 1 is multiplied by y, which equals number 1. Okay, so we might say why we put the minus sign here, because we are choosing x and y as a natural number. If we were taking this one as an integer, which means we are going to plus sign here, put plus sign, because once when you put the integer, we have choice, you can put plus or minus, but if you choose natural number, we must have the minus sign here. Okay, this is the difference. So let's move this stuff to the right. So I get here x is multiplied by n, which equals p minus number 1 is multiplied by y plus number 1. We have another equation here, another statement. So the statement number 3. Okay, so now I think we have enough information here. So what to do here, I'm going to work on the second equation or second statement. Okay, now let's add something here. I'm going to raise both sides to the p minus number 1. Okay, for this statement, let's take this statement 3 to the n, which is a congruent to 1 mod p. Let's raise p minus number 1 as an exponent on both sides. I get 3 to the n p minus number 1 is a congruent to 1 mod p, and also I'm going to switch this exponent on this form, 3 to the p minus number 1 or to the n. So since n is odd, we are going to take off this exponent. So I will have 3 to the p minus number 1 is a congruent to 1 mod p. Okay, so here is the statement number 4 here. I'm going to work on this equation. Okay, let's take this statement here. So I get here number 1, because if you switch the reminders, it will be the same thing. Okay, so I get number 1 is congruent to 3 to the p minus number 1. So I'm going to raise the y as an exponent on both sides, then multiply both sides by number 3. Why I'm going to do that? Because I'm going to get arrived to this statement. Okay, let's multiply both sides by 3. This one I'm going to add it on the exponent. I'm going 3 to the p minus number 1 is multiplied by y plus number 1. Okay, if you take a look carefully here, this one exactly equals x is multiplied by n. So which means this one is going to be congruent to 3 to the x is multiplied by n. Okay, also I'm going to write it on this form: 3 to the n all to the x. As you know, 3 to the n is congruent to minus 1 mod p. Okay, so which means this one minus 1 to the x. So let's check the parity of x. So as you know, right hand side of this equation is a odd, because we get p minus number 1 is a even, because p is a odd. Okay, which means even is multiplied by something, always you get even. Plus number 1 is going to give us odd, which means the left hand side of this equation is also is a odd. Okay, which means the only thing to get odd, since we have the product here, which means odd is multiplied by odd is going to give us odd, which means x must be odd and y is odd. Okay, x is odd. If x is odd, I'm going to take off this exponent. I get minus number 1 here. So get minus number 1 all is congruent to mod p, because I didn't change anything here, because this one is already it was mod p. Okay, all the way down, which means I get 3 is congruent to minus 1 mod p. Notice here we are working on the odd integer, and also here when we start our proof, n it was superior or equal to 3. Okay, because we found n equals 1 as a solution, which means we are seeking for other solution. And also, but remember here, so before we get started, I forgot to put by the way of contradiction. Okay, because our proof, because before we start the proof, we know we are not going to find the solution, which means we are going to go through the absurd proof. We are going to go through by the way of contradiction. Okay, so I get here 3 minus number, I get 3 plus number 1, which is 4, is congruent to 0 mod p. Okay, but this one is not true. We get two different reminders. This one is telling us p divides 4, which is impossible. Okay, this is not true because you have two different reminders. This is clearly, it's a contradiction. What does this mean? Which means we have no solutions. No solutions above this point. Okay, so which means the only solution that we found, which is n equals 1. Okay, so I have finished this proof. Thank you for watching. I will see you in next video. Bye.